Hey everybody, and welcome to chapter 16. We're going to talk about conjugated pi systems today and pericyclic reactions. So as we are looking into this chapter, what's really important for us is understanding resonance. And if you want to review resonance, it's way back in chapter 2, but we hopefully have done a few extra resonance ideas. This unit is going to be all about resonance in specific types of systems. We're going to see paired with this unit aromatic reactions in chapter 17 and 18. All right, so the first thing that we want to talk about is what is a diene? We know the alkene functional group is a carbon-carbon double bond, where both of those carbons are sp2 hybridized as a sigma bond and a pi bond incorporated into that carbon-carbon double bond. Now, a diene, literally two alkenes, and there are three ways that those two alkenes, or the two carbon-carbon double bonds, can be observed in a organic molecule. Cumulated is when the alkenes, the two double bonds, are right next door to each other. So we have an sp2 carbon with an sp carbon and another sp2 carbon. The central carbon where that little dot is the middle carbon holding those two pi bonds. So it's sp hybridized, all right? Cumulated dienes are something that we won't see in reactions, but we do need to be able to identify them. Conjugated is when we have a system of two double bonds that are separated by a single bond. Every atom in that system, the four carbons that I've highlighted there, are sp2 hybridized. That is the class of diene that we are going to be talking about in this chapter. Isolated dienes are a set of two alkenes that are separated by more than one single bond. They are going to be separated by an sp3 hybridized center. Now, out of these, we can see how the conjugated system is a continuous system of overlapping p orbitals. If I just kind of zoom in here, cumulated, because of that central carbon being sp hybridized, remember pi bonds are, if they exist on the same carbon, that central carbon has to have pi bonds that are 90 degrees from each other, because that's where we get the p orbital. The x, the y, and the z plane of the p orbitals are all 90 degrees from each other. So there's no resonance there. Pi bonds are perpendicular, and so there's no conjugation. There's no resonance between those two cumulated pi bonds. Conjugated, they are able to resonate. Notice how this overlapping system of p orbitals is allowing for every p orbital to overlap together. They're all parallel and they're all lined up. Isolated pi bonds are separate. There's no conjugation, there's no resonance, because there's this brick wall right here of the sp3 hybridized center. Now, this chapter is going to again focus on conjugated systems and the special properties that they have with them. Heteroatoms may be involved in a conjugated system. We'll see that later on in chapter 21 as well. So you could have two pi bonds that aren't necessarily carbon-carbon double bonds, right? They could be carbon-oxygen double bonds, or as we see over here also on the right-hand side, carbon-nitrogen double bonds. How do we make them? Well, that's a great question. Preparation of conjugated dienes comes from looking at sterically hindered bases that can be used to make a terminal double bond, right? So just looking at something like 1,3-butadiene over here, 1,3-butadiene, naming not required, but when we're looking at how did I name that, we should make sense. It's a butyl group. It's a 4-carbon chain on carbons 1 and carbon 3. If we're counting left to right there, that's where the double bonds start, and there are 2 of them, diene there. If we had a 2 leaving groups, right, we can make 2 pi bonds. We'll practice synthesis when we get together. Now, the single bonds that are part of this conjugated pi system are technically shorter than their typical single bond. And what that is due to is partially to the idea that the carbons of that single bond are sp2 hybridized. We know the sp2 hybridized orbital is smaller than the sp3 hybridized orbital. Remember this type of a chart. The more S character you get, the closer that orbital is to the nucleus, and so the shorter the orbital, and so the shorter the sigma bond will be. We also see that in terms of stability, conjugated dienes are more stable. One pi bond reacting to hydrogenate, right, to form a single bond, to add two hydrogens, takes or releases negative 254 kilojoules. If we think about the double bond, we see that there's actually a 15 kilojoule difference. So when hydrogenating two alkenes, two isolated alkenes, it's actually releases more energy than two conjugated dienes. And so what that means is that the conjugated system must be lower in energy starting. And so we want to investigate that in terms of why is it more stable? What is it about these dienes that are conjugated? What gives them more stability? So let's look at just a practice problem real quick and finding the conjugated system. So take a minute and find the conjugated one here, and we'll be able to rank these in terms of understanding what is stable or unstable. Pause the video if you need to. Okay, this one first is the most stable. Why? Because when we're looking at the stability of conjugated systems, the more conjugation that we have, the more stable. All right, and so this one has 3 pi bonds all stable. And then we'll look at these two. I'm going to highlight them 2 different colors. There's 2 pi bonds here that are stable, and there's 2 pi bonds here. Let's do them different. That are conjugated. Both B and C have conjugated systems. There's less conjugation, but what we want to be able to decide here is substitution. Remember, mono-substituted alkenes are less substituted than di-substituted alkenes, and they're less stable than tri-substituted. So looking at this is a tri-substituted alkene. It's got 3 carbon groups. This is a di-substituted. Over here we have a tri and a tetra. So B is the second next stable, right? So if this was number 1, most stable, this one's number 2. Because of the more carbon groups attached to those carbon-carbon double bonds, they are more stable. Then C would be number 3, because it does have conjugation, but it is less substituted. And then finally, number 4, least stable, no conjugation. Generally, sigma bonds can freely rotate. All right, so there are some conformations that we can talk about, rotational conformations. These don't make different compounds. These are just looking at the molecule, how it can freely rotate. In the previous question, there was no free rotation because all those dienes were in a cyclic structure. But in a 1,3-butadiene structure, we do have free rotation around this sigma bond, right? And so we will see 2 different types of rotation. The S sigma, cis, where the sigma bond is rotating so that the 2 dienes are on the same side, versus the S trans. Again, S stands for sigma rotation, right? And the cis and the trans is identifying where are the 2 double bonds attached to that sigma bond. All right, so we're looking at that idea. Now, p orbitals are conjugated in these 2, right? But what we really want to be able to identify is in reactions, which one do we want? Is there a better one? Trans will always be lower in energy than cis because of the steric hindrance. We can understand that from all of the previous examples we've had about trans versus cis conformations. However, that doesn't mean that we will be using trans all the time. All this means, and this energy diagram shows, is that the idea of trans is lower in energy than cis. Doesn't say anything about reactivity. The highest conformer is the one of the rotation, right? Thinking about rotating this between the two conformations when actually the conjugated system gets broken, which is why we see a transition state that's higher in energy. Little bit of MO theory review. When two p orbitals come together to make a pi bond, remember bonding lowers the overall energy of a molecule. So we start here with two p orbitals. When they come together to make a pi bond, that pi bonding molecular orbital is lower in energy than the original two p orbitals, right? We do, though, see that there is an anti-bonding orbital. There is that option. When two things come together, two things have to come out of it. That's just basic math. And so MO theory is going to be talking about what happens to those anti-bonding orbitals. Now, this is one pi bond. In conjugated systems, we have 4 p orbitals. So technically, we have 4 molecular orbitals coming out, right? And so we have 4 options for the arrangement of these orbitals. And when we're looking at these 4 options, right, we do bring 4 p orbitals together. Each one has an electron. And when we put them in the molecular orbitals, that's why we fill the lowest orbitals first, right? And 2 electrons in each, opposite spins. We will be talking about the lower orbitals here that are filled and the higher orbitals that are unfilled. But what we do see is that there's full conjugation here in this lowest energy option. And then there is one node in the second option here. We call these psi1, psi2, psi3, and psi4. They are understanding that we are solving the Schrodinger equation, and the Hamiltonian operator of psi1, 2, 3, and 4 are our mathematical operations for molecular orbital theory. Now, when we look at this orbital diagram, I do not need you to memorize it, but I do need you to understand that with an increase of energy, we are decreasing the conjugation. We are decreasing the overlap of the orbitals. The 4 electrons in butadiene will occupy the lowest energy MOs. We know that the off-bow principle says build up from the bottom up, right? And the Pauli exclusion principle says that no 2 electrons can have the same spin and orbitals. So we do see the half up arrow and the half down arrow in each of these. All right. MO theory just is offering an alternate explanation why the central carbon-carbon single bond is shorter and stronger than the typical carbon-carbon single bond. There is part double bond character we see in this first psi1, and then there is single bond character in psi2. So it's somewhere in between a double bond and a single bond for that middle carbon-carbon single bond. Yes, we can think about 3 pi bonds, a hexatriene, and we see that the only thing I really want us to see here at this point in our lives is that when we have 6 p orbitals, 1 electron in each, we get 6 options for molecular orbitals, right? There is that 6 to 6 relationship. All right, now, the reactions that molecules can undergo can often be explained by studying their frontier orbitals. Their frontier orbitals are going to be the ones that are in the middle. From the filled, I'm going to put a line right here. We're going to zoom in. This is the highest occupied molecular orbital, or HOMO. All right, HOMO stands for highest unoccupied molecular orbital, right? MO. LUMO is the next one above it, right? The lowest unoccupied molecular orbital. These frontier orbitals are important because when we are studying how these electrons get excited or interact with light or heat, we actually can interact the HOMO and the LUMO together. With electronic excitation, such as shining light on a molecule, we can actually excite an electron from the HOMO up into the LUMO. What that does is it creates a new HOMO and LUMO. It creates a new reactivity because now the electron exists in psi4 when it originally existed in psi3. This is what we're going to be practicing. Right now, what we want to be able to understand is looking at a basic diagram, can we see the HOMO and the LUMO? And when we think about electronic excitation, can we predict the new HOMO and LUMO? So conjugated systems can absorb UV or visible light. We're going to bring up a few extra things before we dive too far into molecular orbital theory, okay? Before we get into reactions, we want to talk about these electronic excitations and how they interact with things like spectroscopy, all right? So we just came from spectroscopy of nuclei in NMR and bonds in IR, and now we're going to talk about conjugated systems and how do they interact with spectroscopy. So conjugated systems can absorb UV or visible light. What happens is one of the outermost electrons in the original HOMO can get excited into a higher energy state. Light energy is converted to potential energy so that it allows that ground state electron configuration to become an excited state. In general, the necessary energy to excite the electron from a pi to a pi star, the HOMO to the LUMO, falls within this UV vis region, all right? So we talked about that region and the energy. It's a little bit more energy than what we've been dealing with from the radio and the infrared, right? We're shooting down the electromagnetic spectrum into a more higher energy state. UV vis spectroscopy gives structural information about a molecule, just about the light energy absorbed. It's looking at an absorbance. So we would see a spectrophotometer would be able to measure the amount of absorbed energy by the conjugated pi system. You've done spectrometry before in general chemistry when you looked at colored transition metals. This is the same type of thing. Now, the only thing is that the more conjugated the system, the smaller the gap between the HOMO and the LUMO, the pi and the pi star. So the smaller the energy gap, the greater the wavelength. And so we can start to see two systems, two pi bonds conjugated is usually absorbs energy around a lambda, a wavelength of 217 nanometers. The longer our conjugated system, the higher the wavelength because the energy gap is getting smaller. Remember, energy is equal to hc over lambda. As lambda increases, energy decreases, right? It's inversely proportional. We will have the Woodward-Feser rules for understanding what lambda max we can predict. This is another mathematical style operation. This would not be using UV vis to predict a structure. All we are going to be able to do with these rules is look at a structure and predict the lambda max, predict the color region, what region of the UV vis spectrum is the molecule going to absorb. Now remember, groups of atoms that respond to absorbing UV light is actually known as a chromophore because they have color. And so it's really looking at this color spectrum, which we'll talk about in just a little bit, that is helpful for us in looking at a real life molecule and understanding what color does it actually absorb, and therefore what color do we see in our eyeballs. So we will be using the Woodward and Fieser rules that were developed to predict the lambda max. Let's look at them now. So they estimate the lambda max. It's not a perfect estimation, but it's pretty gosh darn close. For a conjugated dyene, there are 5 rules that we're going to do. Here's the first 3. This is table 16.4. All conjugated systems, we're going to talk about the simplest one, which is 1,3-butadiene, 2 double bonds conjugated, right? They have a base value of 217. So we'll always start with 217 nanometers. For each additional double bond, 1, 2 here in this example, we'll add 30. All right, so if you take the base 217 and in this structure of our octatetraene, right, 4 conjugated pi bonds here in this molecule, we would say 2 times 30. So the observed or the predicted lambda max was 277 when we add 60. Observed is 290. That's pretty close. Oxochromic alkyl groups. These are branches off of sp3 carbons. All right, they don't have to be methyls. They're just alkyl groups connected to the actual chromophore, connected to the actual carbon-carbon double bonds. How many bonds do we have branching off? In this example, we have 3. And so we would say 3 times 5 and add it to the 217. Each one of these examples is taking it individually. We'll see an example overall in just a little bit. An exocyclic double bond is going to be any of the double bonds that are existing outside of a ring. Okay, so an exocyclic means that one carbon is in a ring and the other one not in the ring. This doesn't happen often, but it does sometimes happen. What we observe in that type of exocyclic double bond is that we need to add 5. 1 position in the ring, 1 position outside of the ring. Usually we see add 5 nanometers to the base. Now, when we're looking at this lovely diagram, we also have 2 of our oxochromic alkyl groups, all right? So that was 5 as well. So the 2 alkyl groups that are attached to this conjugated system and the 1 exocyclic double bond, all right? This next guy, a homoannular dyene, meaning that they are in one ring, boop, boop, boop. Right? There's the 1 ring and it's locked in an S-cis conformation. When that happens, we add 39. And don't forget 1, 2, because these are connected. 1, 2, 3, 4 of our oxochromic alkyl groups. So we see 4 times 5 for the alkyl groups, 39 for the homoannular dyene. So let's take a little practice here when we're looking at this chromophore, all right? So I'm gonna start, and like always, lots of colors. Here's my base, 217, and I'll highlight it green. We have a conjugated system, beautiful, so 217. I have 2 extra pi bonds that are conjugated as well. So add 30, so 2 times 30 for those extra pi bonds. And we're going to add this all up, this big old long chain of stuff. Now, I do have 1, 2, 3, 4 oxochromic alkyl groups. So for that, we have 4 sp3 carbons branching off to finish the alkyl group, so 4 times 5. And so we'll add this up. 217 plus 60 is 277, plus another 20, 4 times 5, 297 nanometers for this guy. All right, we'll practice more together when we get into class. Now for the fun bit, where is all of this visible spectrum and how does it relate to us? Highly conjugated compounds absorb light in the visible region of the electromagnetic spectrum, which was 400 to 700 nanometers. And so common things like lycopene and beta carotene are naturally occurring compounds that look like colored compounds. So beta carotene specifically is what we're going to talk about here. It is the compound that is attributed to the orange color in a lot of fruits and vegetables like carrots, sweet potatoes, mangoes, cantaloupe, whatever, you name it. If it's orange, it most likely has beta carotene. Beta carotene is known to be good for your eyes, and to really understand why, we have to understand what happens to beta carotene in your body. It's the imine formation that plays an important role in this process. We're going to talk about what that means a little bit later on in chapter 19. However, when we observe color, the color observed by your eyes is actually the opposite of what is required to cause the pi to pi star excitation, right? And so when we see orange, it's really because the opposite is occurring in terms of the excitation. The absorbance of color in beta carotene is blue. The absorbance is in the blue spectrum, so it reflects orange into our eyeballs. Now, rods and cones are the photosensitive cells in our eyes that are attributed to detection of light and detection of color. So rods actually are talking about the magnitude or the intensity, I suppose, of the light. Cones are what are responsible for color. And beta carotene can actually be decomposed and metabolized, let's make it a biological term, metabolized in the liver to produce vitamin A, which is also called retinol. And so retinol, here's beta carotene, and it is metabolized to form vitamin A or retinol. Retinol or vitamin A is then oxidized, and one of the double bond undergoes isomerization. So specifically, this oxygen is oxidized to an aldehyde, which is why we're going to talk about it again in chapter 19. And also, this double bond isomerizes to a cis instead of a trans carbon-carbon double bond. That resulting aldehyde can actually react with an amino group on a protein called opsin. And that amine group reacting with the aldehyde forms an imine. We're going to talk about this compound a little bit later on, again, chapter 19, but it's that imine group that is photosensitive. So rhodopsin can absorb a photon of light, initiating a photoisomerization of the cis double bond back to the trans, and that resulting change actually triggers a signal that is ultimately detected in the brain and interpreted as vision. So yes, not only beta carotene, but vitamin A is very important for our vision. It's that vitamin A that then is isomerized to the cis conformation, cis retinol, and then reacts in our cones to detect color, right? And to detect light. And that is interpreted in our brain as vision. If you have a deficiency in vitamin A, it can actually lead to night blindness, which is a condition that prevents the eyes from adjusting to dimly lit environments. Super important, all these conjugated pi systems. And so it's specifically identifying the calcium +2 ion channels. And so it's really, our eyes are extremely sensitive, and just a few photons can cause this isomerization to occur and create a nerve impulse that we see as vision.